A modern cargo ship can weigh tens of thousands of tons, yet it floats in a fluid environment that constantly tries to flip it over. The ability to recover from this rolling is called transverse stability. When a ship leans to one side, we have to identify the cause of the tilt. If the vessel is pushed over by external environmental forces, like a heavy wind or slamming waves, that temporary inclination is called a heel. If the vessel is leaning because of forces inside the ship, such as improperly loaded containers or shifting heavy machinery, that permanent fixed inclination is called a list. To predict whether a ship will safely snap back from a heel or slowly capsize from a list, marine architects reduce the entire massive of steel hull down to exactly 4 theoretical geometric points. A ship's survival at sea is dictated by the dynamic mathematical relationship between gravity pulling down and buoyancy pushing up. This schematic begins at the absolute bottom of the hull with K, the keel. It serves as the baseline for measuring vertical heights. Above the keel is B, the center of buoyancy. This is the center of the underwater volume, where displaced water pushes up. Next is G, the center of gravity. This is the concentration point of the ship's mass, hull, fuel, and cargo, where gravity pulls straight down. When a ship rests perfectly upright, buoyancy pushing up and gravity pulling down are aligned on the vertical centerline. Finally, we identify M, the metacenter. This is the theoretical pivot point that the ship swings from when it begins to roll. The distance between the center of gravity and the metacenter is called the metacentric height, or GM. We calculate this by taking the height of the metacenter and subtracting the height of gravity. As long as the center of gravity remains strictly below the metacenter, the vessel possesses positive initial stability, generating the righting forces needed to snap back upright. Consider a practical operational scenario. A 10,000-ton cargo ship has an initial height of gravity at 6.0 meters and a metacenter at 7.0 meters. During operations, a 200-ton piece of machinery is shifted diagonally from the lower porthold to the starboard main deck. To recalculate the ship's stability, this complex diagonal movement is isolated into 2 independent mathematical vectors, a vertical shift and a transverse shift. Step 1 involves analyzing the vertical vector. The machinery was lifted exactly 5.0 meters upward. To find the vertical shift of the overall center of gravity, we multiply the weight of the cargo by the distance moved and divide by the total displacement. Multiplying 200 tons by 5.0 meters and dividing by 10,000 tons results in a 0.1 meter upward shift. We add this shift to the original 6.0 meter height, resulting in a new overall height of gravity of 6.1 meters. The new metacentric height is found by subtracting the new gravity height from the constant metacenter height. 7.0 minus 6.1 gives 0.9 meters. Hoisting that 200-ton weight upward physically dragged the ship's center of gravity higher, squeezing the vessel's GM stability margin down to 0.9 meters. Step 2 focuses on the transverse vector of the shift, noting that the machinery was moved 10 meters horizontally from port to starboard. We apply the shift formula for transverse movement. 200 tons multiplied by 10.0 meters, divided by the 10,000-ton displacement. The ship's overall center of gravity is pulled 0.2 meters off the centerline toward the starboard side. Because gravity is now pulling downward from an off-center position, it creates a listing moment that forces the entire hull to tilt. As the hull tilts, the center of buoyancy slides outboard until it aligns underneath the new gravity point, G1. Step 3 is calculating the exact angle of list, theta, using trigonometry. The trigonometric formula for the angle of list states that the tangent of theta equals the transverse shift divided by the metacentric height. To find the true angle, you must use the squeezed, newly calculated GM of 0.9 meters rather than the original baseline. We insert our calculated values into the formula, 0.2 meters divided by 0.9 meters. This results in a tangent ratio of approximately 0.2222. Calculating the inverse tangent reveals that the ship will settle into a permanent 12.5-degree list to starboard. Moving heavy cargo diagonally rewrites the ship's equilibrium, reducing its ability to fight waves while locking it into a permanent transverse tilt. The specific magnitude of a positive GM dictates how a ship behaves dynamically in open water. A stiff ship is one possessing a comparatively large GM distance. This large GM creates powerful righting moments, causing the ship to snap back to the vertical position quickly and aggressively. While stable, these rapid rolls cause severe structural fatigue on the hull and damage cargo lashings. In contrast, a tender ship operates with a comparatively small GM margin. A small GM generates weak righting moments, resulting in a sluggish rolling period that is comfortable for the crew, but offers a narrower margin of stability. Operational safety requires managing GM to ensure the rolling period is neither too violent for the hull nor too sluggish for stability. What happens if cargo is shifted so high that the center of gravity rises entirely above the metacenter? This state is unstable equilibrium. With a negative GM, righting forces are lost and the ship cannot remain upright. Any slight external force causes the ship to roll deeper into the water, as gravity pushes the vessel away from the center line. An unstable ship eventually reaches an angle of lull, the point where it stops falling and catches its equilibrium at a permanent tilt. The hull's deep tilt radically changes the underwater shape, forcing the center of buoyancy to swing far out toward the low side. The roll only stops when the buoyancy moves far enough outboard to align perfectly underneath the center of gravity, eliminating the capsizing moment. Correcting unstable equilibrium requires lowering the effective center of gravity, which can be achieved by lowering weights already on board, loading new weight below G, or discharging weight from above. Understanding the mathematical interplay of K, B, G, and M allows a mariner to diagnose a tender ship before it reaches a state of instability.